While Einstein was trying to understand the universe, he hinted at possibilities that no one else dared to consider. Today, we are right in the middle of those possibilities, parallel universes. Perhaps somewhere else, another version of you is living a completely different life. So has this crazy idea really entered the realm of science? By the way, liking my video and subscribing is the most effective way to support me. If you also mention where in the world you're watching from and what time it is, I really enjoy reading those comments. 1. Einstein's objection to quantum and the opening of the door to multiple universes. Einstein never internalized the randomness of the quantum world and sought a deterministic order in the deep structure of nature. This quest created a climate of inquiry that, while seemingly fighting quantum, actually increased the possibilities for alternative explanations. The question of whether there are hidden variables behind randomness or whether the apparent probability is the shadow of a higher structure took root here. The Copenhagen interpretation's acceptance that measurement determines reality was a cold solution for Einstein. However, the multiverse idea, which states that the physical counterpart of every branch opened in measurement occurs in other worlds, transformed randomness into the branching of reality, unexpectedly opening a door to Einstein's desire for order. Thus, the objection became fertile ground that nourished its own opposite. The reasoning established in the EPR thought experiment brought to the fore the problem of simultaneity, which could not be explained in a single universe. The assumption that if reality is not locked into a single past, branching histories could make measurement paradoxes less contradictory gained strength. This made alternative universes a logical option at the point where chance escaped mathematics and seeped into physics. Today, there is no complete consensus on the quantum interpretation. Nevertheless, Einstein's persistent skepticism has driven some physicists to seek the structure behind probability in broader frameworks, such as the multiverse. This quest promises a wider range of explanations, rather than being confined to a single universe. 2. Clues to the multiverse in the field equations of general relativity. General relativity presents a geometric theory of space-time curved by matter and energy. These equations allow for multiple solution families under certain conditions, and some extreme solutions give rise to cosmic structures indicating relatively independent regions. When mathematics does not insist on a single solution, the idea that physics may not be confined to a single stage gains strength. Headlines such as closed time-like curves and exotic energy conditions whisper that it may be possible to construct different universe scenarios on a global scale without disrupting local consistency. The goal here is not to create miracles, but to honestly measure how far the equations open the doors. As the boundaries expand, it is not imagination but the equations themselves that suggest new scenarios. Relativity alone does not necessitate a multiverse. However, when combined with efforts to merge with quantum mechanics and early universe conditions, some solutions of the equations point to bubble-type universes. Not everything mathematics allows must be real, but the map of what is possible becomes increasingly detailed. These clues do not constitute direct proof. Nevertheless, the flexibility of the field equations significantly influences the direction of research, implying a catalog of options unfolding in a phase space rather than a single cosmic narrative. This influence keeps alive the motivation to search for measurable traces. 3. Cosmic inflation, necessitating the bubble universe scenario. Inflation is an extremely rapid expansion phase in the early universe that lasts only a very short time. The field triggering this phase can settle at different speeds in different regions, leading to the formation of bubble universes that are causally disconnected from each other. The same fundamental physical principles yield different local outcomes. Some inflation models point to infinite processes. New bubbles are born in continuous expansion, and each bubble carries its own local constants and history. The universe we observe in this picture is just one bubble in a vast foam. Inflation has achieved some observational success. The smoothness of the cosmic background and certain spectral features support this picture. However, it is difficult to find direct traces of events like bubble collisions, and this difficulty continues to test the strength of the explanation. The seemingly difficult search for traces is not in vain. If inflation is the origin, it may have left fingerprints such as unexpected symmetry breaks or statistical anomalies on a cosmic scale. Once these traces are found, the bubble scenario ceases to be an abstract idea and becomes a testable hypothesis. 4. Cosmic traces that could arise from the collision of universe bubbles. If bubble universes approach each other, collision fronts form. These fronts can lead to observable anisotropies by rearranging energy flows and geometry. Circular half-shadows or asymmetric wave fronts may be expected in the cosmic background. The statistical power of such traces is important. This is because they are likely to be mixed with random fluctuations in the background. For a solid detection, not only the presence of the pattern but also its detailed signature is required. Collision scenarios can also cause slight variations in local physical constants. Such a deviation could produce clues such as very weak shifts in the fine structure constants measured in different parts of the sky. If these shifts are reduced to expected sensitivities, the measurement window opens. Current maps do not show a clear collision signature. However, as sensitivity increases, the field of possibilities narrows and certain models are eliminated. This elimination alone is a powerful scientific gain that makes the picture credible. 5. Alternative explanations for anomalies in the cosmic microwave background. Cold regions and alignment patterns that appear to deviate from statistics in the sky are occasionally discussed. Some of these may be measurement biases, but some may point to real cosmic structures. The alternative universe traces hypothesis is just one of the candidates at this point. A single model may not be sufficient to explain the anomaly. Inflation parameters, early universe phase transitions, or astrophysical contamination may also play a role. A robust result emerges from the competition of different explanations. Improvements in data quality determine the lifespan of anomalies. If the deviation is real, its shape is preserved in subsequent maps, and its statistical power increases. In this case, a stage is set for testing new physics, including multiverse scenarios. If the deviation fades, the model simplifies, and standard cosmology gains strength. Both outcomes are valuable because either a new door opens or false doors close. Science advances when curiosity is combined with balanced patience. 6. New universe births beyond the singularity of a black hole. General relativity becomes fragile at singularities. When quantum gravity corrections come into play, finite density cores that could replace singularities and new expansion phases derived from these cores are theoretically possible. In this picture, the end of one universe could be the beginning of another. The information paradox takes on new meaning in this scenario. If information flows into a different structure, it changes form rather than ceasing to exist. A possible universe birth could transform this flow into a physical corridor. It is not possible to map the interior of a black hole observationally. Nevertheless, this idea can be tested indirectly through expected signatures in regions close to the event horizon. Evaporation residues and mass spectra play a key role here. When black holes are considered not only as scenes of destruction, but also as birthplaces, the cosmic timeline ceases to be unidirectional. This approach does not provide direct evidence for the multiverse idea, but it builds a logical bridge and enriches the research path. 7. The possibility of Einstein-Rosen bridges as inter-universe passages. Wormholes are bridge geometries permitted by the equations of relativity. Exotic energy conditions are required for them to be stable and traversable, and these conditions cannot be provided by classical matter. Whether quantum corrections can close this gap is an open area of research. The existence of a bridge does not necessarily mean a gateway to another universe. However, tunnels connecting different regions on a cosmological scale could potentially bring regions with different physical constants into contact. If this contact produces measurable small deviations, the idea becomes testable. Time and causality become complicated with wormholes. If information transfer and the energy budget are not balanced, the model quickly becomes inconsistent. Therefore, not only the existence of the geometry, but also its thermodynamic compatibility is tested. If a picture emerges in which bridges can be permanent and secure on a cosmic scale, the multiverse moves away from being merely a philosophical possibility. An observational sign is required for such a picture, and today's telescopes are gradually becoming sharper in order to search for this sign. 8. Explaining the quantum measurement problem with the multiverse. Quantum theory works with probability amplitudes, and a single result is observed in measurement. The multiverse interpretation suggests that every possible outcome that appears in measurement occurs in different branches. Thus, the concept of branching replaces randomness. This approach requires a reinterpretation of the concept of probability. When amplitude weights are considered as the relative weights of worlds, statistical laws align with long-term experiments. This perspective clarifies how experimental results should be interpreted. The main criticism of this interpretation is its direct testability. The question remains, if there is no interaction between worlds, how can the distinction be demonstrated? Some research mathematically explores the possibilities of weak interactions. Any framework that solves the measurement problem offers a compelling proposal about the nature of reality. The multiverse is one such proposal, adding a coherent narrative to the seemingly puzzling structure of quantum mechanics. The power of the narrative will be evident in the measurement battle it will engage in with rival interpretations. 9. Quantum entanglement and inter-universal connections. Entanglement strongly links the outcomes of distant particles. This connection is not classical communication, but organizes the statistical structure as a whole. In some conceptual frameworks, this wholeness touches on the multiverse picture by representing the shared past of different branches. How entanglement networks behave on a cosmic scale is not yet clear. Measurable remnants of entangled structures from the early universe may exist today, appearing as large-scale correlation patterns. These patterns can be identified by deviations from classical randomness. Entanglement plays a decisive role in the black hole information paradox. If information is not lost, the topology of the entanglement structure may be changing. When topological change is linked to inter-universe scenes, new testing ideas emerge. The claim that entanglement establishes inter-universe connections is not a ready-made conclusion, but an invitation to research. As quantitative measurements become sharper, The response to this invitation will become clearer. Each new experiment makes the invisible threads of the web a little more visible. 10. Different values of physical constants and selection. Parameters, such as the fine structure constant and the cosmological constant, determine the architecture of the universe. Some theories suggest that these constants are not fundamental, but take their values based on local minima in a deeper field. Different minima correspond to different universe scenarios. If the constants are variable, habitability windows are confined to narrow regions. Life and structure formation are only possible within specific bands. This situation brings an explanatory selection effect to the fore. The idea of selection is not proof in itself. However, it provides an alternative explanatory channel for the fine-tuning of parameter values. While this channel does not directly link the multiverse picture to observation, it enhances its plausibility. If future measurements approach the sensitivity to test parameter shifts in different regions of space, the picture changes. Even the smallest shift can strengthen this picture by pointing to a dynamic origin. When motion lies behind what appears to be static, research gains momentum. 11. The Higgs field and frozen universes at different minima. The Higgs field acts as a background field that gives mass to particles. If there are multiple wells in the field's potential, different bubbles can freeze in different wells. This freezing completely changes the mass architecture and chemistry. Some minima may be stable, others semi-stable. In a semi-stable universe, a rare tunneling event rewrites all of physics. This mixture of danger and curiosity provides a powerful motivation to better understand the conditions of the early universe. Different minima give rise to different stellar life cycles. Heavy element synthesis and even chemical bond types may change. In such diversity, life may sprout in very different ways, or not at all. As the Higgs landscape map is drawn, it becomes clear which minima are physically accessible. This clarification gives concrete geometry to the multiverse picture. If this geometry produces testable predictions, the idea passes the experiment test. 12. A multiverse-originated view of dark matter and dark energy. Dark matter forms an invisible gravitational skeleton. If there are weak interactions or extra fields between universes, the observed density distributions may show small deviations. These deviations are sought in the anomaly patterns of large-scale structures. Large-scale velocity patterns, called dark flows, attracted attention for a time. When such patterns are associated with the gravitational shadows of different regions of the universe, alternative explanations arise. Solid data either supports or refutes this relationship. Dark energy drives the accelerating expansion of the universe. The value of this acceleration may differ in different bubbles, and this difference is a reflection of the inflation-originated landscape. Understanding the statistical distribution of this value means conducting a deep cosmic demographic study. As the nature of the dark sector is illuminated, the multiverse hypothesis either gains additional strength or is constrained. In either case, science wins because the right door cannot be found without closing the wrong ones. In this process, the sky becomes a laboratory. 13. Cosmic strings and the interuniverse wall hypothesis. Cosmic strings and field walls may form as remnants of symmetry breaks in the early universe. These structures shape space-time not on a microscopic scale, but on a cosmic scale. Walls behave like boundaries, separating different phase regions. If different phase regions have different physical parameters, the walls become boundary lines separating two universe-like orders. Such boundaries can leave observable signatures through lensing effects and wave scattering. These signatures are among the targets of today's and tomorrow's telescopes. The tension and distribution of strings produce specific wave packets on the cosmic background. The strength of the signature plays with the parameters, which means scanning the model space. Each scan eliminates certain regions and makes the remaining area clearer. The wall and string hypothesis does not directly prove the multiverse. However, demonstrating the reality of the phase landscape reveals the infrastructure of the multiverse picture. When the infrastructure is visible, the seriousness of the upper layers increases. 14. The holographic principle and reflections of parallel universes. The holographic principle states that information content scales with surface area. This idea implies that some universes may have equivalent descriptions on subdimensional surfaces in other formulations. Equivalence makes the idea of different scenes for the same physics natural. If different scenes carry the same dynamics, unexpected affinities may be found between parallel universes. Kinship emerges when a single measurement in an experiment allows for different interpretations. This permission points to the existence of a mathematical mirror. Holography is a framework supported by black hole thermodynamics. The storage of information on horizons does not contradict the multiverse narrative and may even build bridges. The idea of bridges becomes concrete when based on testable equivalences. This principle is not merely a conceptual game. Computable model examples have been produced, and some predictions have been compared with experimental data. As the comparisons mature, the mathematical basis of the parallel universe picture strengthens. 15. Could the flow of time be different in different universes? The microscopic mechanism that determines the direction of time has not been fully resolved. While entropy increase provides a general rule, the details raise open questions. It is a logical possibility that the arrow of time could proceed differently in bubbles with different initial conditions. Regions where the arrow of time is weak can be imagined in some universes. In such regions, processes proceed without distinction between forward and backward, and the macroscopic order is completely different. This order fundamentally changes the scheme of chemistry and life. The different perception of the speed of time is already known through relativity. Within the framework of the multiverse, this diversity is linked not only to local conditions but to the entire history of the universe. When the connection is made, the same physics results in different historical timelines. This flexibility in the picture of time keeps the search for observational signs alive. Early universe fossils and cosmic processes that act as clocks are the tools of this search. As the tools become sharper, it becomes clearer whether time is universal or local. 16. The connection string theory establishes with multi-dimensional universes. String theory proposes that the fundamental particles in the universe are not point-like, but vibrating strings. This theory not only presents a new particle model, but also states that extra dimensions are inevitable in the mathematics of nature. Reality, which appears to be confined to 3 spatial and 1 temporal dimension, may actually be the surface reflection of a broader stage with 10 or 11 dimensions. This is precisely where the idea of parallel universes gains scientific ground. Some of the extra dimensions are hidden from our view, but universes with different physical laws may exist in the depths of these dimensions. Mathematical solutions show that these universes are not merely a possibility, but a necessary consequence. Each of these multi-dimensional universes could have different physical constants, different types of particles, and completely different cosmic histories. What we consider universal, the speed of light, the gravitational constant, or the mass of an electron, could have completely different values in these universes. In this case, while life may be impossible in one universe, extraordinary biological diversity may be observed in another. Each vibration mode corresponds to the possibility of a new universe. Just as different notes on a musical instrument create different melodies, different vibrations of strings give birth to different universes. In this picture of string theory, we hear only one melody, but countless melodies may be playing simultaneously in the cosmic orchestra. The curving of strings in extra dimensions is another point of curiosity. Theoretical physicists describe these curvatures using abstract geometries called Calabi-Yau manifolds. These manifolds come in countless different shapes, and each shape determines the physical laws of a different universe. In other words, universes are not just possibilities, but mathematical necessities. Whichever curvature is chosen, a universe corresponding to it is born. The Calabi-Yau structure of our universe even determines how atoms and stars are formed. It is impossible for a hypothesis with such a strong connection to mathematics not to arouse curiosity. However, the most striking aspect is that this theory is still far from experimental proof. For now, the existence of strings cannot be directly observed, but the extra dimensions predicted by string theory may reveal themselves through massive accelerators, like the Large Hadron Collider, or through hidden signatures in cosmic background radiation. If these signatures are detected, parallel universes will cease to be scientific fiction and will be accepted as inevitable consequences of nature. 17. Universes born and dying within the quantum foam. Although space-time appears smooth as a fabric on a macroscopic scale, at the Planck scale, it is like a boiling foam, composed of infinite fluctuations. This foam is formed by the instantaneous creation and annihilation of virtual particles. These microscopic fluctuations are powerful enough to create and destroy not only particles, but entire universes. Universes are born, live, and then fade away, like bubbles in a quantum foam. Our universe may be just one bubble that rose up within this foam and managed to survive. These micro-universes that emerge in the quantum foam usually collapse rapidly onto themselves. However, rarely does one expand sufficiently to become stable and continue its evolution as an independent cosmos. Our universe could be that exceptional bubble that managed to survive after billions of attempts. This perspective removes the notion of our universe's existence as a miracle, and instead presents it as an inevitable outcome in the sea of possibilities. This is one of the most fascinating ideas about the origin of the cosmos. The foam universe idea is not merely theoretical speculation. It is a natural outcome of some cosmological models. Quantum tunneling processes, fluctuations in vacuum energy, and uncertainties arising at the Planck scale provide mathematical support for this idea. Thus, a picture of universes merging and dispersing like foam is consistent with both relativity and quantum mechanics. If this picture is correct, our universe is not unique, but merely one of an infinite number of cosmic foams. Today, scientists are indirectly searching for traces of this quantum foam. Abnormal patterns in cosmic background radiation, small deviations in vacuum energy density, or microscopic signatures arising from black hole evaporation could be clues to the backstage of this foam. If these clues are ever confirmed, the story of our universe's birth will be completely rewritten. 18. The possibility of quantum tunneling creating inter-universe passages. Quantum tunneling is the ability of particles to overcome obstacles that they cannot pass through classically. This phenomenon has been observed countless times in laboratories. For example, electrons pass through semiconductors in this way. Now, when we scale this simple phenomenon up to the universe, the question that comes to mind is, could an entire universe tunnel into another vacuum state? If so, inter-universe gateways may be hidden at the heart of quantum mechanics. Tunneling from one vacuum to another could suddenly change the physical constants of the universe. This would fundamentally transform the structure of that universe. One universe could fade away through its own tunneling, while another universe could be born through the same process. This idea makes the concept of a multiverse even more dramatic, because universes are not merely side by side, but constantly replacing each other. The universe itself may be operating like a giant quantum tunneling laboratory. The possibility of tunneling is mathematically supported. The existence of metastable vacuums in field theories, combined with fluctuations in the quantum foam, opens the door to the birth of new universes. Thus, tunneling becomes a process that determines not only the fate of particles, but also that of entire cosmoses. This perspective tightly links cosmology with the most fundamental laws of quantum physics. Of course, observing these processes is nearly impossible. However, there are some indirect signs, uncertainties in the vacuum energy of the universe, the stability of the Higgs field, or the behavior of dark energy. If our universe is in a metastable vacuum, one day it could tunnel into another universe. This possibility is as frightening as it is fascinating. 19. Different histories and civilizations in parallel universes. The idea of a multiverse is not limited to the laws of physics. If there really are an infinite number of universes, each one may have followed a different course of history. In one universe, humanity may never have experienced the Industrial Revolution. In another, the Roman Empire may still be standing. In yet another, the Earth may never have formed. Every possibility is a reality in the cosmic catalogue of diversity. This perspective shows that history is not a single-line destiny, but a branching forest. Every choice, every possibility becomes reality in a different universe. Our history is just one of the branches in this forest. This adds a new dimension to the debates about free will and destiny. Our choices have actually been made and not made, experienced with different outcomes in different universes. If civilizations develop differently in different universes, scientific progress may also have different stages. In some universes, quantum mechanics may have been discovered 1,000 years ago, while in others, the wheel may not have been invented yet. This diversity suggests that humanity's universal reasoning capacity is not limited to a single example. Such a picture cannot, of course, be directly observed. However, mathematical probabilities and the flexibility of physical laws do not allow these ideas to be logically dismissed. Curiosity remains alive here at the intersection of philosophy and science. To think that our history is not unique is both chilling and fascinating at the same time. 20. The possibility of quantum computers exchanging information with other universes. Quantum computers promise processing power beyond that of classical computers by exploiting the superposition and entanglement properties of particles. According to some interpretations, these devices may include not only the possibilities of our own universe, but also those of other universes in their processing. In this case, quantum computers would be exchanging information with parallel universes without realizing it. Although this claim is still controversial, it opens a logically fascinating door. If every possible solution occurs in a different universe, the quantum computer may actually be pulling the answers from these universes, and bringing them to our own. Such a mechanism explains the increase in processing speeds that cannot be compared to classical machines. The strongest argument supporting this idea is that quantum computers actually behave differently from classical machines. The speed increases observed in experiments may carry the shadow of parallel universes. Of course, this is not direct proof, but it makes the multiverse interpretation more appealing. If it is ever confirmed that other universes play a role in the operation of quantum computers, it will fundamentally change not only technology, but also our perception of reality, because then we would have to accept that in every calculation, in every algorithm, we are witnessing an inter-universe collaboration. 21. Dark energy, originating from pressure differences between parallel universes. Dark energy is accepted as the source of our universe's accelerating expansion, but its nature remains a great mystery. When Einstein added the term he once called the cosmological constant to his equations, he was actually making a necessary move to show the universe as static. Although he later admitted this was a mistake, this concept of a constant plays a key role in understanding dark energy today. However, there is a more intriguing possibility here. Perhaps this energy is not an intrinsic property of our universe, but arises from a pressure difference between our universe and others. In other words, the accelerating expansion of our universe could be the manifestation of a cosmic push coming from a neighboring universe. This perspective suggests that a mathematical term Einstein added 100 years ago could be the gateway to a much greater truth. Cosmic inflation theories show that vacuum energy can take on different values. If each bubble universe has a different vacuum density, they could be connected by cosmic membranes. If there is a pressure difference between the density of another universe and ours at the edge of our universe, the effect of this difference could be felt as an acceleration inward. This acceleration could be the accelerating expansion we observe. Such a picture transforms Einstein's cosmological constant from merely a mathematical correction into an indicator of an inter-universe dynamic interaction. The power of this idea lies in placing the observed phenomena in a new context, because today we only have one number to explain dark energy, approximately 70% of the universe's energy density. But we don't know where this number comes from. If this number is the result of a pressure difference from neighboring universes, then dark energy becomes the signature not only of our universe, but of the relationship between universes. More precise measurements of dark energy in the future may provide an opportunity to test this hypothesis. The polarization patterns of the cosmic background, the distribution of large-scale structures, or deviations in supernova observations could reveal this pressure difference. If such evidence is found, the cosmological constant, which Einstein once called my biggest mistake, could actually go down in history as an inter-universe window. 22. Quantum superposition as possible evidence for parallel universes. One of Einstein's biggest objections was the randomness of quantum mechanics. When he said, "God does not play dice," he meant his belief that the most fundamental laws of nature did not operate like a roulette table. However, the phenomenon known as quantum superposition makes it possible for a particle to exist in multiple states simultaneously. This has been repeatedly tested and confirmed in laboratories, but the real question is this superposition merely a mathematical expression of probabilities, or does each possible state actually occur in a separate universe? If the second possibility is correct, quantum mechanics becomes direct proof of parallel universes. The fact that an electron can be in both an up and down spin state, or that a photon can be both here and there at the same time, actually means that the universe branches out into every possibility. These branches are separate from each other, and each develops as its own universe. Einstein was skeptical of this idea because he did not accept chance. But ironically, the most powerful solution proposed to go beyond chance is the multiverse interpretation, which he rejected the most. Today, even the working principle of quantum computers is based on this superposition. Computers can calculate billions of possibilities at once because particles can exist in multiple states. Some physicists suggest that this process could be a kind of computational support for possibilities occurring in parallel universes. If this is true, then every time a quantum computer operates, we are actually interacting with other universes. This is a possibility so radical that Einstein would not even have dared to imagine it. Of course, the problem of proof arises here, too. It is nearly impossible to directly test whether superposition is universe branching or just probability waves. But small anomalies in quantum experiments, unexpected deviations in decoherence processes, could provide clues. 23. The possibility of other universes being born inside black holes. Einstein's theory of general relativity predicted the existence of black holes, but what the inside of these objects looks like has always remained a mystery. At the point called the singularity at the center of a black hole, the laws of physics break down, and mathematics becomes meaningless. However, quantum gravity corrections suggest that this singularity could actually be the birthplace of a new universe. In other words, every black hole could be a gateway to another universe. Even our own universe may have been born inside a black hole in another universe. This idea shows that black holes can be creative as well as destructive. When a star collapses, it closes in on itself. But the extreme density formed at the center may give birth to a new space-time bubble. This bubble is completely separated from our universe by the event horizon and begins to develop as a universe in its own right. In such a case, black holes are like universe factories. If Einstein had seen this idea, he would probably have been very curious, because his equations actually allow for such a possibility. Einstein-Rosen bridges suggest that other universes may exist on the other side of black holes. So black holes are not just cosmic graveyards, they can also be birthplaces. This perspective opens a new window for understanding the continuity of the universe. Finding observational evidence is very difficult because we cannot look inside a black hole. But black hole evaporation, Hawking radiation, and small anomalies in the cosmic microwave background could provide ways to test this idea. If one day evidence is found that black holes truly gave birth to the universe, Einstein's equations will be regarded as a sacred text explaining not just this universe, but the birth of an infinite number of universes. 24. Anomalies in the cosmic microwave background being traces of cosmic collisions. The cosmic microwave background, CMB, a remnant of the universe's birth, covers the entire sky like an echo of the Big Bang. The fact that this radiation is largely uniform is a major success of the inflation theory combined with Einstein's general relativity. However, there are small but noticeable irregularities within this map. Some regions are colder than expected, while others show unusual alignments. Whether these anomalies are too pronounced to be explained by ordinary chance has been debated for years. This is where the possibility arises that other universes may have collided with our own. If such collisions did occur, traces of these events could be imprinted in the fabric of the CMB. When universes, expanding like balloons, collide with each other, Energy flows occur in these collision regions. This energy could cause small but measurable distortions in the development of our universe. Circular traces, symmetry breaks, or unexpected cold spots in the CMB could be signs of these collisions. The famous cold spot, seen in the cosmic microwave background, is one of the strongest candidates associated with such explanations. Perhaps this spot is the shadow of another universe falling onto our own. Einstein's equations of relativity may seem to disallow direct interaction between universes. However, these equations contain multiple solutions, and each solution can represent a different cosmic scenario. If Einstein had witnessed such anomalies, he might have interpreted them not as a flaw in his theory, but as a sign of a larger cosmic structure. Because his concern was always to understand the universe as a whole, the incompatibility of the parts was, in his view, a harbinger of a deeper unity. Today, the Planck satellite and other observatories have mapped these anomalies in minute detail, yet there is still no definitive interpretation. If it is later understood that these irregularities truly stem from cosmic collisions, this would not only confirm the existence of parallel universes, but also add a completely new chapter to the history of our universe. 25. Einstein's quest for a unified field theory opened the door to the idea of multiple universes. Einstein spent the last 30 years of his life pursuing a unified field theory that would combine all the forces of nature into a single equation. For him, nature could not be the sum of fragmented laws. Even gravity and electromagnetism, seemingly separate, were different facets of a deeper unity. However, this endeavor had an unexpected consequence. The equations allowed for the simultaneous existence of not just one universe, but many. Einstein did not mention this possibility because his goal was the search for unity, not plurality. Nevertheless, when the doors of mathematics opened, the seeds of the multiverse possibility had been sown without his knowledge. The biggest problem encountered in the unified field effort was that the equations offered completely different solutions under different boundary conditions. While one solution reflected the laws of our universe, another pointed to a completely different cosmos. This diversity complicated Einstein's goal of a single universe, single law approach. Looking back today, we see that this mathematical multiplicity actually paved the way for the concept of parallel universes. It showed that the universe was not bound to a single inevitable solution, that one equation could make many universes possible. Einstein's contemporaries struggled to understand his insistence. While turning his back on the probability-based world of quantum mechanics, he was actually seeking a much broader explanation. If he had accepted the multiple solutions offered by his equations, perhaps we would refer to the idea of multiple universes by his name. But Einstein pursued order, simplicity, and uniqueness. His stubbornness paved the way for other physicists to evaluate these solutions. Ironically, the orientations Einstein rejected played a significant role in the birth of multiple universes. Today, string theory, quantum field theory, and cosmology continue Einstein's dream of a unified field in different forms. Each brings together different aspects of nature under one roof, while also showing that countless universes are possible. If the existence of multiple universes is ever truly proven, Einstein's name will again be at the center of this story, because he set out believing that there was a single mathematical divine order underlying the universe. But this belief ironically opened doors pointing to much more than a single universe. 26. Parallel universes hold secrets about the nature of time. For Einstein, Time was the most fundamental stage of relativity. He removed time from being absolute and made it a dimension dependent on the observer. But the origin and direction of time still hold unsolved mysteries. If parallel universes really exist, the flow of time may be different in each one. Time may flow faster in one universe, run backwards in another, or perhaps not exist at all in yet another. Such diversity suggests that time is not a single reality, but a property that varies from universe to universe. The most fascinating aspect of this idea is that it makes the order of time in our universe more understandable. In our universe, entropy constantly increases, meaning time always flows forward. But in another universe, entropy could decrease, and processes could run backward. In this case, something that is past for us could be future in another universe. This possibility suggests that time is not an absolute law, but a choice dependent on the nature of the universe. In Einstein's own words, the distinction between past, present, and future is only a stubborn illusion. He wrote this sentence after the death of his friend Michele Besso, but it also reflected a deep philosophical view of the structure of the universe. If parallel universes truly have different time orders, Einstein's words are not just a metaphor, but a real physical explanation. Because time may indeed be an illusion, but the form of the illusion is different in each universe. Testing this idea is not easy. Still, quantum fluctuations, the black hole information paradox, and cosmic inflation models can help us understand whether time is universal or local. If one day traces of different time arrows are found, it would mean not only the multiverse but also the nature of time has been solved. By the way, liking my video and subscribing is the most effective way to support me. 27. The bending of the second law of thermodynamics in different universes. In our universe, the second law of thermodynamics is absolute. Entropy, or disorder, increases over time. This law is the most fundamental compass that determines the direction of time. But in other universes, this law may work differently. Perhaps in some universes, entropy decreases. Perhaps in others, it remains constant. Perhaps it fluctuates. In this case, thermodynamics, which we consider immutable, is actually not a universal law, but a local one. Einstein's theory of relativity showed that the laws of nature can vary depending on the observer. This perspective suggests that even the second law of thermodynamics could yield different results in different universes. If the multiverse is correct, the increase in disorder in our universe may be merely a local feature. In other universes, the spontaneous emergence of order and the formation of complex structures without expending any energy may be possible. Such a picture also has striking implications for the nature of life. In our universe, life is built on energy imbalances. Energy from the sun enables living things to transform into ordered structures. But in another universe, with a decreasing entropy, life could develop through a completely different mechanism. In this case, life would be not just a biological miracle, but a thermodynamic one. Although proving this hypothesis is difficult, cosmological experiments examining early universe conditions could shed light on the origin of entropy. If entropy is not universal, this would be one of the strongest signs of parallel universes. Einstein's doubts about the nature of time take on a direct physical meaning here. 28. The infinite possibilities of multiple universes. Einstein believed that the universe had a comprehensible and orderly structure. In his view, nature was written in the language of mathematics, and this language contained a precise order. However, the idea of multiple universes completely overturns this order. Because if there are an infinite number of universes, every possibility has been realized. In one place, a different law of physics, in another a different history, in yet another, a completely different form of life. The cosmos is not a single story, but a library of infinite stories. This idea is both fascinating and frightening, because then our universe is not special, but just one of infinite possibilities. What we call luck or chance is actually a natural consequence of infinity. Everything has happened, everything will happen, everything has surely happened somewhere. This picture takes the debates about free will and fate to a whole new dimension. Because every choice we make has been made differently in another universe. Would Einstein have accepted such a picture? Perhaps not, because he was always in pursuit of order. But he also liked to explain the seemingly incomprehensible aspects of the universe within a broader context. If the idea of an infinite universe is truly an inevitable consequence of nature, Einstein would try to understand it rather than reject it, because for him, science was attempting to understand God's thoughts. And perhaps God's thoughts were the thoughts of an infinite number of universes. There is no experimental proof for this idea, but mathematics, cosmology, and quantum mechanics do not rule out this possibility. In fact, in some theories, this result becomes inevitable. If one day, even indirectly, evidence of the existence of infinite universes is found, it will be one of the greatest breakthroughs in human history. 29. Resolving time travel paradoxes with multiple universes. Einstein's theory of relativity showed that time is not absolute, but relative. The slowing of time for an observer traveling at speeds close to the speed of light is clearly seen in the twin paradox. However, there are also solutions that theoretically allow time to flow backwards. These solutions bring paradoxes with them. If you go back in time and kill your grandfather, how will you be born? This is where the idea of multiple universes comes in. Perhaps time travel does not disrupt the consistency of a single universe, because every intervention in the past splits the universe into branches. This perspective eliminates the paradox. In one universe, your grandfather survives and you are born. In another universe, your grandfather dies and you never exist. In this case, time travel does not break and destroy a single story. It merely creates a new one. Einstein did not speak directly about time travel, but the solutions to his equations did not rule out this possibility. If he were alive today, he might accept the mathematical elegance of the multiverse idea in solving these paradoxes. The most fascinating aspect of time travel debates is that they also involve the concept of free will. If every journey creates a new branch, then no choice truly conflicts. This picture provides a different answer to Einstein's desire to explain the universe with a single grand equation. The equation may be singular, but its solutions are manifold. Each solution is a universe, each universe a timeline. Today, physicists are examining mathematical solutions such as closed time-like curves. There is no observational evidence yet, but if time travel experiments can be conducted one day, their results could directly test the idea of multiple universes. Einstein's name will remain at the center of these debates because his equations show that time does not only flow forward, and that mathematics allows for different scenarios. 30. Quantum fluctuations, triggering the birth of universes. One of the most intriguing outcomes of quantum physics is that the vacuum is not truly empty. Particle-antiparticle pairs are constantly being created and annihilated within the vacuum. This microscopic fluctuation could even lead to the birth of universes on a macroscopic scale. In other words, our universe may have emerged as an exceptional result of quantum fluctuations. This perspective brings together the geometric stage indicated by Einstein's equations and the uncertainties of quantum physics. Fluctuations may seem ordinary on a small scale, but when the energy density is large enough, they can give birth to a new bubble universe. This bubble rapidly expands and becomes a cosmos in its own right. If our universe is also the product of such a fluctuation, then the origin of the universe is not a miracle, but a natural consequence of quantum physics. Considering Einstein's skepticism towards quantum mechanics, this picture would have been disturbing to him, because quantum randomness explains the existence of universes. Quantum fluctuations also influence the structure of the universe we observe today. Small irregularities in the cosmic microwave background are direct traces of quantum fluctuations in the early universe. Without these traces, galaxies would not have formed. Thus, the large-scale order of the universe is a product of quantum chaos. This paradoxical situation challenges Einstein's statement that God does not play dice, because the architecture of the universe does indeed appear to depend on the rolling of dice. In the future, more precise measurements may further clarify the relationship between these fluctuations and the birth of the universe. If it becomes certain that new universes can arise from quantum fluctuations, then cosmology will become inseparably integrated with quantum physics. The unified theory Einstein envisioned could become a reality at this point. Uncertainty and certainty become two sides of the same equation. 31. Energy densities transforming into completely different forms in different universes. Einstein established the link between energy and mass with his famous equation ELMC2. This equation shows that energy and matter are actually different manifestations of the same thing. However, the idea of multiple universes suggests that this relationship may operate differently from universe to universe. While energy transforms into specific particles in our universe, completely different types of particles may emerge in another universe. This difference is crucial in terms of the existence of life. This is because our biology is based on carbon and water-based chemistry. If the energy-matter conversion produced different particles, life as we know it could never have existed. Perhaps there are silicon-based life forms in another universe, or perhaps no form of life is possible. Einstein's quest for universal order is tested here again, because in his view, the laws of nature should be singular. But the idea of multiple universes suggests that each universe has its own laws. The fact that energy densities take different forms in different universes may also explain the cosmological constant problem. In our universe, the cosmological constant is very small, but not zero. If this constant were slightly larger, galaxies would not form. In the multiverse scenario, there are countless universes where this constant takes different values. We are only in the habitable one. This is one of the strongest interpretations of the anthropic principle. In the future, it may not be possible to observe the energy forms of different universes, but mathematical models increasingly support this possibility. Einstein's equations, while explaining the energy-matter relationship, did not point to a single universe. Multiple solutions opened the door to multiple universes. This was an unexpected result of his quest for a unified field. 32. Our universe being just an ordinary bubble within the infinity of the universe. Einstein initially believed the universe was static, but when Hubble's observations showed the universe was expanding, he had to abandon this idea. As far as we know today, the universe is constantly expanding. But according to the idea of multiple universes, our universe is just an ordinary bubble within this infinite expansion. There could be countless other bubble universes around us, and we are completely unaware of their existence. This idea further diminishes humanity's place in the universe. In the Copernican revolution, we learned that the Earth was not at the center. Later we learned that the Sun was not at the center either, and that our galaxy was ordinary. The idea of a multiverse takes this revolution to its ultimate conclusion. Even our own universe is not special, but merely one of infinite possibilities. Einstein viewed this idea with both admiration and skepticism. For him, nature should be understandable, but the multiverse offers an infinite catalog of possibilities rather than a comprehensible whole. Nevertheless, this idea solves many cosmological problems. The fine-tuning problem, dark energy density, the cosmological constant. All become meaningful within the framework of the multiverse, because we exist only in the habitable bubble. This perspective removes our universe from being special and makes it a statistical outcome. It is difficult to trace these bubbles observationally. But at the edge of our universe, traces of collisions with other universes may be found. If such evidence is ever obtained, it will be understood that our universe is indeed an ordinary bubble. This will shake Einstein's understanding of the universe once again, but it will also make the greatest contribution to his search for the bigger picture. 33. The forward-backward flow of time can vary between universes. Einstein's theory of relativity made the speed and direction of time dependent on the observer. However, in our universe, time always flows forward. This is because entropy constantly increases. But in another universe, entropy could decrease, and time could flow backward. In this case, our past could be the future in another universe. This idea is not merely philosophical, but a physical possibility. In quantum mechanics, some processes have time symmetry. That is, they can proceed in the same way in both forward and backward directions. If such processes dominate in a universe, time flows backward rather than forward in that universe. Einstein would have struggled to accept such a scenario, but his equations would allow for it. This is because his equations do not necessitate the unidirectional flow of time. The fact that time flows differently in different universes also changes the debate on free will. Perhaps the choices we make have already been made in another universe. Perhaps something that will happen to us in the future has already happened in another universe. This scenario suggests that time is not absolute, but rather a property that varies from universe to universe. Although it is difficult to test this idea observationally, quantum gravity theories suggest that time is not a universal property, but a local one. If traces of different time arrows are ever found, it will explain not only the multiverse but also the nature of time itself. Einstein's biggest question, what is time, will then find its answer. 34. The impact of parallel universes on discussions of fate and free will. Einstein was a determinist. For him, the laws of nature were fixed and unchanging. The probability-based structure of quantum mechanics was unacceptable to him. However, the idea of multiple universes takes this debate to a whole new level, because if there really are an infinite number of universes, every possibility has come to pass. In this case, the debate between free will and fate loses its meaning. While we made one choice in one universe, we made the exact opposite choice in another. In one, we have failed. In another, we have succeeded. In this case, there is no such thing as a real choice, only different outcomes in different universes. Einstein's statement, "God does not play dice," is reinterpreted here. Perhaps God does not play dice, but creates every possibility. We, however, live in only one of them. This idea also changes our understanding of responsibility. If every possibility has been realized, how free are our choices? But at the same time, this brings a new definition of freedom. Freedom is not just our journey in one universe, but all our journeys in infinite universes. Einstein's deterministic view expands in this picture, and the laws of the multiverse apply in different ways, in different universes. This seemingly philosophical debate is directly present in interpretations of quantum physics. If different measurement outcomes occur in different universes, then the free will debate also takes on a physical dimension. Einstein's objection is perhaps most ironically resolved here. Nature is not random. It simply operates on a much larger scale. 35. The cosmological constant taking different values in multiple universes. Einstein added a constant to his equations to show the universe as static, the cosmological constant. Later, when it became clear that the universe was expanding, he saw this as an unnecessary addition. But in 1998, supernova observations revealed that the universe is expanding at an accelerating rate, and the cosmological constant reappeared. Now, cosmology suggests that this constant can actually take on different values in different universes. In our universe, the constant is very small, but not zero. In another universe, it could be much larger and might not allow galaxies to form. This perspective explains why our universe has a value that allows life. Because if the constant were slightly different, neither stars nor planets nor life could have emerged. Our universe is just one of the rare bubbles that allow life. In the multiverse picture, there are countless universes where the constant takes on different values. In this case, the existence of our universe is not a miracle, but a natural consequence of probability. Einstein's greatest desire was for the laws of nature to be orderly and understandable. The cosmological constant, appearing to be an arbitrary number, was unacceptable to him. But the idea of a multiverse solves this problem. The number is not arbitrary. It takes different values in different universes. Our universe is simply the one with a value suitable for life. Thus, Einstein's quest for unity paradoxically becomes compatible with the multiverse. Today, it is difficult to test this idea because we cannot directly observe the values in other universes. However, the polarization patterns of the cosmic background, supernova measurements, and the distribution of galaxy clusters may provide clues. If evidence pointing to different values of the constant is ever found, it will lead us to reinterpret not only cosmology, but also Einstein's legacy. 36. The dark flow phenomenon is an inter-universe gravitational effect. In the late 2000s, astronomers discovered that galaxy clusters in certain regions of the sky were moving at an unexpected speed in the same direction. This movement was called the dark flow. Normally, the expansion of the universe should have pushed galaxies apart equally, but some clusters seem to be dragged by an invisible gravitational force. The source of this mysterious phenomenon could be the gravitational pull of other universes outside our own. If neighboring universes truly exist, their mass density could affect our universe. This effect cannot be seen directly, but reveals itself in the movement of galaxies. Einstein's equations of relativity show that gravity propagates at the speed of light. But these equations also imply that different regions of space-time can be connected. Perhaps dark flow is the cosmic scale echo of these connections. This idea suggests that explaining our universe solely through its own internal laws may not be sufficient. Einstein's desire to view the universe as a closed whole is being tested again here. If dark flow is indeed the effect of other universes, then our universe is only a small part of a larger cosmic structure. This picture takes our universe out of being a single stage and makes it one of the scenes in a much larger play. For now, the exact cause of dark flow is unknown, but as observations improve, it may become clear whether this movement is truly related to other universes. If so, this finding will be one of the greatest discoveries in human history, because the galaxies we see in the sky will carry signs not only of our own universe but of other universes as well. 37. Different laws arising from the vibrations of strings. String theory defines the fundamental particles of the universe as vibrating strings. Different vibration modes of these strings correspond to different particles. In other words, the diversity of nature actually originates from a single source, the vibrations of strings. But it doesn't end there. Strings vibrate in extra dimensions that are curved in different ways. When these curvatures differ, the resulting laws also differ. When strings vibrate differently in another universe, the laws of physics there may be completely different from ours. Einstein's quest for unity manifests itself here as well, because his goal was to reduce nature to a single equation. String theory provides a framework suitable for this goal. Everything arises from the vibrations of the same strings. But at the same time, this theory also necessitates the idea of a multiverse, because different curvatures mean different universes. In other words, infinite diversity arises from a single source. This picture removes our universe from being special. Our universe is merely the result of a specific curvature. Other curvatures create other universes. Each universe carries its own laws and experiences its own destiny. If Einstein were to look at this picture, he would probably be fascinated because it encompasses both unity and diversity at the same time. Today, string theory still lacks experimental evidence, but it is mathematically very powerful. If one day traces of the extra dimensions predicted by strings are found, the idea of a multiverse will cease to be speculation. Einstein's dream of unification will thus become a framework explaining the diversity of universes. 38. Inter-universe collisions leading to Big Bangs. According to some theories, our universe did not have a singular beginning. Perhaps it was born from a collision with another universe. When the surfaces of two universes came into contact, the immense energy released could have been our universe's Big Bang. In other words, the Big Bang is not the beginning of the universe, but the result of an inter-universe collision. This idea could answer one of the biggest questions in cosmology. Why did the Big Bang happen? If universes really collide, the Big Bang is not a beginning, but merely a transition. Although Einstein's equations do not directly point to such a collision, the flexible structure of space-time allows for it. This is because his equations are not closed to the merging of different geometries. The collision scenario can also be tested through observations. Circular patterns or unexpected anisotropies in the cosmic microwave background could be traces of such collisions. Some anomalies are already being interpreted in this direction. If evidence is found, our ideas about the origin of the universe will change fundamentally. This picture shows that our universe is not unique, but rather the product of a larger cosmic dynamic. The equations Einstein wrote to understand the universe may be a framework that explains not only our universe, but the entire cosmic history arising from the collisions of universes. 39. Quantum entanglement creating hidden links between universes. Quantum entanglement is the phenomenon where two particles behave as if instantly connected, no matter how far apart they are. Einstein called this phenomenon the spooky action, and approached it with skepticism. But experiments have repeatedly shown that entanglement is real. Now, some theories suggest that this connection may exist not only between particles, but also between universes. If different universes originated from the same quantum root, remnants of entanglement may still exist between them. In this case, the universes are not completely independent, but are connected by invisible strings. These strings could cause very weak effects on a cosmic scale. Clues to this could be sought in the distribution of galaxies, the evaporation of black holes, or correlations in the cosmic background. Einstein would probably have been astonished to see such a picture. For him, nature should be explained by local interactions. But quantum entanglement has shown that nature's much more than local. The idea that inter-universe connections can also be established through entanglement does not confirm his doubts, but expands them. Because understanding the secrets of quantum mechanics may be the same as understanding the secrets of the universe. Today, entanglement has been proven between particles billions of kilometers apart in laboratories. If this phenomenon is also valid on a multiverse scale, the multiverse may no longer be just a theory, but a measurable reality. The effect Einstein called spooky may be the invisible language of the universe. 40. The idea that the universe could be a holographic reflection. The holographic principle, developed since the 1990s, suggests that the universe's three-dimensional structure may actually be the reflection of a lower-dimensional surface. Just like the hologram on a credit card, two-dimensional patterns on the surface can create a three-dimensional image. If this is true, then our universe is also a hologram of another surface. This surface could exist in different dimensions and with different physical laws. In this case, our universe is merely a reflection of a larger cosmic structure. Einstein was one of the first to wonder whether black holes contain information. The equations of relativity state that black holes are merely geometric structures. But quantum mechanics suggests that information must be preserved on these structures. The holographic principle resolves this paradox. Information is not lost. It is encoded on the surface of the black hole. A broader inference can be made from this. Not only black holes, but the entire universe could be encoded on a surface. In this case, we are projections of a deeper reality. This idea becomes even more striking when combined with the idea of multiple universes. If our universe is a hologram, there could be other holograms on other surfaces. In this case, universes could exist not just side by side, but in layers. Each surface projects its own universe, and we are only inside one of them. If Einstein could have envisioned such a picture, he would have realized that his equations could encompass not only a space-time stage, but also the relationships between surfaces. Today, the holographic principle finds strong mathematical support. String theory, black hole thermodynamics, and quantum field theory suggest that this principle could be correct. There is no direct proof yet, but some findings related to quantum information in laboratory experiments point to this idea. If the holographic universe is ever confirmed, the steps Einstein took to understand the universe will take on a whole new dimension, because then our universe will not be reality itself, but the shadow of a greater reality. 41. Cosmic cycles forming a chain between universes. Some cosmologists argue that the universe was not born just once, but was born and died countless times. This idea is known as the cosmic cycle theory. The universe expands, slows down at a certain point, collapses, and is reborn. This cycle continues indefinitely. Each cycle begins with different initial conditions, which can lead to different physical laws and different histories unfolding. Thus, universes are linked in a chain. Einstein believed the universe was static. He did not think the universe was born or would die, but his equations allowed for a dynamic universe. When Hubble's observations revealed that the universe was expanding, Einstein was forced to change his mind on this subject. Today, the idea of cosmic cycles is a modern interpretation of this flexibility offered by Einstein's equations. Traces of these cycles may be hidden in the cosmic microwave background. Perhaps the small anomalies we see are memories left over from the previous universe. If this is true, our universe has risen from the ashes of previous universes. This picture suggests that time is not linear, but cyclical. Einstein's view of time as relative, combined with this idea, gives rise to the notion that time is an endless circle. The cosmic cycle theory has not yet been proven, but it has a strong mathematical foundation. If these traces are ever found, it will be one of the greatest discoveries in human history. Because then, we will understand that our universe does not just have a beginning, but is part of an infinite chain. Einstein's quest for wholeness will take on a whole new meaning in these infinite cycles. 42. Black holes as universe factories. Einstein's equations predicted black holes, but he had doubts in his own mind about what they were. He thought black holes were solutions too strange to be real. Today we know that black holes exist and are the most powerful objects in the universe. But here's the interesting part. Some theories suggest that black holes may not only be destructive, but also creative. Every black hole may be giving birth to a new universe within itself. When a star collapses, a black hole is formed. But during this collapse, the extreme density at the center can give birth to a new space-time bubble. This bubble breaks away from our universe thanks to the event horizon and begins to expand on its own. Thus, every black hole becomes a birthplace for another universe. Our universe may have been born from such a black hole. Einstein would have been surprised if he could have seen such a picture, because his equations actually allowed for this possibility. Einstein-Rosen bridges implied that new universes could exist on the other side of black holes. But for Einstein, these were merely mathematical solutions. Today, these solutions have become one of the boldest hypotheses in cosmology. Proving this idea is not easy. But observations around black holes, findings such as gravitational waves and Hawking radiation, may support this possibility. If it is ever proven that black holes give birth to universes, it will be the greatest turning point in humanity's journey to understand the universe. Einstein's name will once again be at the center of this debate. 43. The existence of different life forms in parallel universes. If multiple universes exist, different laws of physics may apply in each one. Life in our universe is based on carbon and water. But in another universe, silicon-based life could develop. Even stranger, there could be life forms with a completely different chemical basis beyond our understanding. This diversity shows that the universe contains infinite possibilities, not only in terms of physics, but also biologically. Einstein did not directly concern himself with the origin of life, but he always wondered how the laws of nature made life possible. To him, the universe had an understandable order, and this order allowed for the existence of life. But the idea of multiple universes suggests that life is not universal, that it is only possible in certain universes. In this case, Our existence is merely the result of special conditions. This idea also makes biology a part of cosmology, because life is not only a product of molecules, but also of the laws of the universe. Different laws in other universes could give rise to different forms of life. Perhaps in one universe, consciousness has developed entirely on quantum waves, or perhaps in another universe life has never emerged. There may be no direct evidence for this hypothesis. But trying to understand the limits of the universe makes it necessary to consider this diversity. Einstein's belief that the universe has a comprehensible order takes on a new dimension here, because order can manifest itself not only in our universe, but also in countless universes that allow for different forms of life. 44. Explaining the quantum measurement problem with branching universes. In quantum physics, particles exist in multiple states simultaneously until they are measured. When measured, a single result is observed. This paradox has been debated among physicists for decades. The multiverse interpretation offers a radical solution to this paradox. When measured, a single result does not occur. Every possible outcome occurs in a different universe. Einstein always criticized the measurement problem. In his view, reality should not depend on the observer. But the idea of multiple universes takes this criticism in a new direction. Because the single result seen in the measurement is only the share of our universe, other results have occurred in other universes. In this case, the arbitrariness of observation disappears. This perspective also clarifies the statistical laws of quantum mechanics. This is because probabilities are not merely mathematical possibilities, but the shares of real universes. Had Einstein seen such a picture, his skepticism towards quantum mechanics might have taken a different form, because here there is no randomness, only branching realities. 45. The existence of cosmic membranes at the boundaries of universes. Some models in cosmology suggest that universes are separated from each other by surfaces called cosmic membranes. These membranes can be thought of as thin layers that define the boundaries of universes in higher dimensional space. Our universe may also exist on such a membrane in a four-dimensional universe. Beyond the membrane, there may be other universes with completely different physical laws. This idea is based not only on science fiction, but also on the necessary solutions of mathematics. This is because theories such as string theory naturally incorporate multi-dimensional spaces, and membranes become inevitable in these dimensions. If our universe truly exists on a membrane, the movement of this membrane could also determine the fate of our universe. When the membrane vibrates, cosmic ripples occur in our universe. When the membrane collides with another membrane, enormous energy is released, which could trigger a new Big Bang. In other words, the birth of our universe may have resulted from the collision of two cosmic membranes. This scenario presents the beginning of the universe not merely as a singularity, but as the natural outcome of a larger structure. Einstein's general relativity equations, while not explicitly stating this idea, laid the groundwork for it. His equations implied that spacetime is not limited to 3 dimensions, but could also yield solutions in higher dimensions. Einstein might have viewed such an interpretation with skepticism, but its mathematical elegance would not have failed to captivate him. For his greatest belief was that the universe possessed a regular structure, and this order might be hidden in the vibrations of the membranes. Today it is not possible to see the traces of the cosmic membrane hypothesis directly, but such traces can be sought in the large-scale structure of the universe. in the propagation of gravitational waves, or in the behavior of dark energy. If evidence of the existence of membranes is ever found, it will be confirmed that our universe exists only on one membrane, and that other universes exist on other membranes. This would be a revolution that would fundamentally change our understanding of the universe. 46. Universes being part of a holographic multiverse. The holographic principle suggests that although the universe appears three-dimensional, it is actually the reflection of information stored on a two-dimensional surface. This principle was first proposed to solve the information paradox of black holes. But over time, it became a powerful enough idea to be applied to the entire universe. If true, our universe is merely a reflection on a surface. But the truly striking part is that this surface does not belong solely to our universe. It contains the reflections of countless different surfaces, countless different universes. For Einstein, the concept of information was one of the cornerstones of physics. He argued that the universe has an understandable structure. The holographic principle takes this comprehensibility to another dimension. All the complexity we see in the depths of the universe is actually the unfolding of information hidden on a simpler surface. If this is the case, multiple universes become not just a possibility, but a necessity, because different surfaces produce different reflections. This picture redefines the reality of the universe. The world we see may actually be the shadow of a higher dimensional surface. Other surfaces carry the shadows of other universes. Each surface is a self-contained repository of information. The unified order Einstein sought may have lain in these surfaces, because for him, nature must be much simpler and more elegant at its core. Today, research on the holographic principle is converging with string theory and quantum field theory. Mathematics supports this idea, but experimental evidence is still distant. However, future observations of black holes and detailed maps of gravitational waves may reveal traces of this principle. If holographic pluralism is confirmed, the order Einstein sought will have been found, but that order will encompass not a single universe but the shadows of countless universes. I'd like to make a small reminder. If you'd like to support me, you can click the join button below the screen. Your support is truly valuable to me. Thank you in advance. Let's continue with our video. 47. The possibility of the universe being a simulation and its intersection with multiple universes. There is an idea that has become popular in recent years. Our universe could be a simulation. In other words, our reality could be operating within a computer-like structure created by a more advanced civilization. At first glance, this idea may seem unrelated to Einstein's equations. But that's not the case, because Einstein explained the universe entirely through a mathematical structure. If our universe is a mathematical construct, then this construct could be intertwined with other universes. The simulation idea becomes even more powerful when combined with the multiverse. If our universe is a simulation, then other universes could also be other simulations. There could even be another simulation within a simulation. In this case, universes consist not only of physical layers, but also virtual layers. Einstein wrote equations to understand the universe. Perhaps these equations were the expression of our universe's code. This perspective completely changes the concept of reality. Everything we see could be the result of a calculation. But this calculation applies not only to our universe, but to countless other universes as well. When the idea of a multiverse is combined with the simulation hypothesis, reality becomes an infinitely layered structure. If Einstein could have seen such a picture, he might have retained his belief in the comprehensibility of the universe, but he would have said that this comprehensibility meant computability. Testing this hypothesis is difficult, but not impossible. Small anomalies, appearing pixelated, are being sought in the mathematical structure of the universe. If such a trace is found, it would indicate not only that our universe could be a simulation, but also that other simulated universes could exist. Einstein's equations would remain valid even in this scenario, as mathematics speaks the same language across every layer. 48. The possibility of energy exchange between universes. Some physicists believe that universes are not completely independent, and that energy exchange between them is possible. This idea was proposed specifically to explain the mystery of dark energy. Perhaps the accelerating expansion of our universe is the result of energy transfers from neighboring universes. If this is true, universes are connected by invisible veins, and energy flows through these veins. Einstein's equations of relativity made the conservation of energy a universal law. But what if this law is only valid within the boundaries of a single universe? If there is energy exchange between universes, the energy that is lost to us may actually appear in another universe. In this case, the laws of nature are not being violated. They are simply operating within a broader framework. This idea could also explain the mystery of dark matter. Perhaps the invisible matter we observe is the effect of energy leaking from other universes. If Einstein could have seen this picture, he would have realized that his equations encompassed not just a single universe, but the larger system of universes. His quest for unity would have found its true meaning in such a multi-dimensional structure. Today, there is no proof for this hypothesis, but small anomalies in cosmological observations, the unexpected behavior of dark energy, and changes in the universe's acceleration rate may point to this idea. If one day it is truly understood that there is energy exchange between universes, this would take Einstein's legacy to a new dimension. His equations would explain not only our universe, but also the invisible veins between universes. 49. Mathematics necessitating universes. Is mathematics merely a creation of the human mind, or is it the very fabric of the universe? This question has been debated for centuries. Some physicists argue that mathematics is not just a tool, but the fundamental fabric of reality. If this is true, each solution to a mathematical equation could be a separate universe. There is no single solution to an equation. Each parameter produces a different result. Some of these results may have created our universe, while others may have turned into other universes. In other words, the multiverse is the inevitable consequence of mathematics. What makes this idea even more striking is the astonishing consistency of the abstract world of mathematics. The human mind independently constructs an equation, then looks at the universe and finds the answer to that equation. Maxwell's equations predicted electromagnetic waves, Einstein's equations predicted black holes, and Schrödinger's equation predicted quantum behavior. If mathematics is such a powerful prophetic tool, then the solutions to mathematics that we have not yet seen may also have their counterparts in other universes. This door that mathematics opens to the idea of multiple universes removes our universe from being special. We are merely living in one of the solutions to certain equations. Other solutions led to other universes. This picture further diminishes humanity's place in the universe, but it also offers a fascinating perspective. We are a page in mathematics' infinite book. There are other pages, and they are all writing their own universes. Scientists are examining what they call the landscape of solutions in mathematics to make this idea concrete. Theories such as string theory produce trillions of different mathematical solutions. If each solution is a universe, then the multiverse is not just a possibility, but a mathematical necessity. Such a picture shows that at the heart of nature lies not chance, but the rigid necessity of mathematics. 50. Quantum consciousness as the gateway to multiple universes. The origin of consciousness remains one of the greatest unsolved mysteries. Some theories argue that consciousness arises not only from biological processes, but also from quantum processes. If this is true, consciousness may be directly linked to multiple universes. This is because quantum superposition is a process where possibilities branch out. The branching that occurs in the brain's microtubules or in the quantum interactions of nerve cells may allow consciousness to touch parallel universes. This perspective makes the human mind not separate from the rest of the universe, but directly connected to it. Our thoughts do not occur in just one universe. Different versions of ourselves in other universes also produce different thoughts. In this case, consciousness is like a symphony echoing across universes. We only hear one note of this symphony, but other notes are playing in other universes. This idea, which reconciles consciousness with multiple universes, also redefines free will. Because every choice produces not just one outcome, but countless different outcomes. The decision we feel is only one version of one universe. Other decisions have already been made in other universes. This picture allows us to see consciousness not just as a biological byproduct, but as a universal connection. There is no proof of quantum consciousness yet, but some experiments suggest that quantum effects may play a role in the brain. If this proves true, consciousness could be the first internal observation window opening onto multiple universes. To understand the secrets of the cosmos, we may need to look not at telescopes but at our own minds. 51. The universe as an information processing network. There is an increasingly accepted idea in physics. The universe is fundamentally processing information. The smallest building blocks of matter and energy can actually be thought of as units of information. Just like the bits of a computer, the universe may have an infrastructure made up of qubits. In this case, the universe consists not only of matter and energy, but also of information flow. If this is true, different configurations of information give rise to different universes. This perspective adds a new dimension to the idea of multiple universes, because information can be organized in countless ways. Each organization creates a different universe. If our universe is the result of a specific information organization, other organizations correspond to other universes. The cosmos is a vast information processing network, and we are a small node in it. Einstein saw the universe as an understandable order. He did not consider information to be fundamental, but his search for order is actually consistent with the idea of information. Because without information, there is no order. If universes are different arrangements of an information landscape, then the equations Einstein wrote to understand the universe were merely describing different arrangements of information. Today, quantum computers and information theory are beginning to concretize this idea. The information paradox in black holes shows that the universe is defined by information. If it is ever proven that the universe is truly an information processing network, the multiverse will become not only a physical reality, but also an informational one. 52. The rarity but inevitability of life. In the context of the multiverse, the origin of life is still not fully explained. Life on Earth emerged when the right conditions came together. But how rare were these conditions? Some scientists say that life is an incredibly low probability. If so, the existence of life seems miraculous. However, the idea of a multiverse explains this miracle. If there are an infinite number of universes, the emergence of life, however rare, becomes inevitable. We are only in the universe where life exists, because otherwise we couldn't ask this question. This perspective reinforces the anthropic principle. The existence of life depends on the fine-tuning of the universe. The physical constants have very precise values. If these values were slightly different, there would be no stars, no planets, and no biochemistry. In the multiverse scenario, these constants take different values. We exist only in the universe where life is possible. In this case, life is rare, but also inevitable. Einstein did not deal directly with biology, but he sensed that the order of the universe made life possible. For him, the universe had to be understandable because it had an order that could be comprehended by the human mind. The idea of a multiverse takes this intuition to a new dimension. Life being understandable only emerges in universes that allow life. Our universe is one of the members of this elite club. This idea suggests that life is not only a biological necessity in the cosmic context, but also an existential one. If there are an infinite number of universes, life must emerge somewhere. We are merely witnesses to this reality. This picture makes humanity's place in the universe more modest, but also more meaningful, because life is one of the inevitable products of the cosmic landscape. 53. The diversity of the initial conditions of universes. The Big Bang theory states that our universe originated from a hot and dense point. But no one knows why the initial conditions were precisely this way. If the density had been slightly less, the universe would have immediately dispersed. If it had been slightly more, it would have rapidly collapsed. The idea of a multiverse solves this mystery. Different universes are born with different initial conditions. Our universe is just one of the balanced ones. Other universes may have collapsed before they even formed, and some may have dispersed without ever forming stars. This picture takes away the uniqueness of our universe, because the perfection of the initial conditions is not a miracle, but a statistical selection. Among countless universes, only the balanced ones survive. Einstein believed in the order of the universe, but this order does not have to arise from a single beginning. Perhaps order is hidden within diversity. Today, cosmologists search for traces of these initial conditions in the cosmic microwave background. The distribution of fluctuations is evidence of small differences at the moment of the universe's birth. If the multiverse is correct, the diversity of these fluctuations may be experienced in completely different ways in other universes. We only see our own version. This idea changes our perspective. Our universe is not unique and sacred. It is an ordinary option arising from the multiplicity of initial conditions. This perspective may be unsettling, but it is also liberating, because our existence is not a miracle, but the result of natural diversity in the sea of universes. 54. Cosmic consciousness hypotheses and the connection between universes and the mind. In recent years, some physicists and philosophers have debated whether the universe is not only a material structure, but also carries a dimension of consciousness. According to this hypothesis, consciousness is not a random byproduct of the universe, but a fundamental component. If this is true, multiple universes contain not only physical, but also mental diversity. Each universe could harbor a different form of consciousness. This perspective places the human mind not at the periphery of the universe but at its center. Our consciousness could be a window through which the universe itself attempts to understand itself. If other universes have different types of consciousness, their ways of perceiving the universe would also be different. What is physical for us may be a directly experienced reality for them. Einstein did not attempt to explain the nature of consciousness, but he believed that what makes the universe understandable is the understandability of the human mind. This intuition aligns with the idea of cosmic consciousness. Perhaps the diversity of multiple universes is not only the diversity of matter, but also the diversity of consciousness. Each universe produces a different fabric of awareness. There is no experimental evidence yet, but the relationship between quantum physics and consciousness is being investigated. If one day consciousness is truly accepted as a fundamental component of the universe, the idea of multiple universes will become a central topic, not only in physics but also in philosophy and metaphysics. 55. Seeing time as an illusion and the multiverse context. Einstein's statement that the distinction between past, present, and future is only an illusion has been much debated. This perspective shows that time is not absolute. When combined with the idea of a multiverse, the notion that time is an illusion takes on even greater meaning. Because time may flow differently in different universes, or may not even exist at all. The fact that time is an illusion leads us to view the universe as a static structure. Just as all frames exist simultaneously in a film reel, all moments exist simultaneously. What we perceive as flow is our consciousness experiencing these frames in sequence. In other universes, this sequence could be completely different. This picture fundamentally changes our thoughts about free will, destiny, and existence. Because if time is not real, choices take on a different meaning. What is yet to come for us has already happened in another universe. Time is merely a product of perspective. Today, theories such as quantum gravity and string theory suggest that time may not be a fundamental property. If this is confirmed, Einstein's intuition will prove correct. The idea of multiple universes reinforces this intuition, because accepting that time is experienced differently in different universes is much more meaningful than a single universe perspective. 56. Universes having different physical constants. In our universe, values such as the speed of light, Planck's constant, and the mass of an electron are very precise. If these values were slightly different, stars would not burn, planets would not form, and life would be impossible. The idea of a multiverse explains this precision because in other universes these constants are different. We only exist in the universe with the constants that make life possible. This idea removes the uniqueness of our universe, because the fact that the constants have values that are suitable for life is not a miracle, but a natural consequence of the multiverse. Among infinite possibilities, some universes allow for life. Our universe is one of them. Einstein expected nature's laws to be elegant. But this elegance lies not in the values of the constants, but in the mathematical framework that makes them possible. The idea of a multiverse expands this framework, because even if the constants are different, the mathematics remains the same. Nature plays different melodies in each universe, but the instrument is always the same. Today, physicists are trying to explain the values of these constants. There is no definitive answer yet, but the idea of multiple universes is a strong candidate for solving this question. If confirmed, the order Einstein sought would be found, but this order would manifest itself not in a single universe but in countless universes. 57. The debate over whether universes exist independently of consciousness. Many philosophers and physicists have questioned whether the universe is independent of the observer. Quantum mechanics shows that observation changes the outcome. This raises the question of whether the universe can exist independently of consciousness. The idea of a multiverse offers a different answer to this debate. Every possibility occurs. Observation merely determines which universe we are in. This picture places consciousness at the center of the universe. Our choices have not only personal, but cosmic consequences, because every choice leads to the birth of a new universe. In this case, consciousness becomes not only a perceiving, but also a creating force. Einstein believed that the universe existed independently of consciousness. For him, the universe was a reality independent of the observer. But the idea of a multiverse challenges this view. Perhaps the universe multiplies along with consciousness. In this case, Einstein's understanding of order merges with consciousness's power to create the universe. There is no definitive proof yet, but quantum experiments keep this debate alive. If a direct link between consciousness and the multiplication of universes is ever found, it will fundamentally change both philosophy and physics. What we see while searching for the secrets of the universe is how little we actually know. The idea of parallel universes fundamentally changes not only cosmology, but also the meaning of existence. Perhaps we are travelers walking along only one path among countless possibilities. Each step we take branches into different scenarios in other universes. This thought diminishes us on the one hand, while reminding us that we are part of something immense on the other. And the most striking aspect is that this mystery continues to deepen, because without understanding the fabric of the universe, we cannot fully understand ourselves. As we close the video, we must remember this. The idea of parallel universes reminded us of the existence of infinite possibilities, but the source of these possibilities may be closer than we think. Because what determines the behavior of the universe at its smallest scale is nothingness, which appears to be completely empty. This nothingness is actually like a boiling sea. Particles appear and disappear in it in an instant. If even emptiness is boiling with overflowing energy, perhaps this is the birthplace of universes. At the end of the video, I put a video on the end screen. Quantum fluctuations. How do particles appear in nothingness? There, you will see how particles are born from nothingness, and perhaps you will get one step closer to the secret of the universe. If you enjoyed this journey, don't forget to like the video, comment, and subscribe to our channel. With your support, we can grow this community filled with science and discovery. Share your thoughts with us because discovering the unknown together is always more exciting. As Carl Sagan said, reality may be stranger than we imagine. Science is the most powerful way to understand this strangeness.